According to Vasari, design are composed only of lines, which so far as the architect is concerned, are nothing else than the beginning and the end of his art. For all the rest is merely the work of carvers and masons. Well, forwarding the notion of autonomous robotic stone carving, we will present three capacities that stand at the core of autonomous craft. In this context, the increasing role of robots in architecture indicates a potential shift from the Anthropocene era, defined by the human shaping of the built environment, to an era in which this environment is shaped by the autonomous machine. This calls for examining the protocols and processes guiding these tools, as well as developing a greater sensibility and a more nuanced relationship between humans and robots. Such a sensibility always stood at the core of craft, in which there's a direct relationship between the human, the tool, and the processed material. However, as digital fabrication increased the influence of the tool in forming objects, it physically distanced the human from the material in the making process of these objects. This is often viewed as a signal of the demise of manual techniques, provoking fear of their replacement by autonomous machines. In contrast to that, we argue that industrial robotic arms can introduce new human-tool relationships. These relationships feature increased sensibilities to the material and the production environment. The acceleration of industrialization correlates with the rise of automated tools in architecture. In this context, our lab explores ways in which digital fabrication can integrate high-skill domains into automation and construction. However, despite this progress, current robotic tools still fall short of addressing custom, high-skill tasks, as well as in handling uncertain conditions and materials. This limitation is rooted in the nature of existing automated machines, which are mainly single-task in their orientation. We present here autonomous carving, drawing on recent research on traditional regional stone dressing techniques and their adaptation to robotic fabrication. In this context, three capacities enable robotic tools to autonomously perform craft: documenting, augmenting, and enhancing the robotic fabrication process. For this purpose, we envision a practice in which the robotic arm could be taught to react to a specific material scenario, similar to the way a craftsman would. However, as high-skill tasks cannot yet be fully automated, there is a continued demand for skilled craftsmen to perform complex stonework, such as carving delicate features, three-dimensional patterns, and more. The advantages of a human craftsman in their ability to negotiate with the material and overcome conditions arising from the inherent uncertainty of the stone. This is achieved by real-time decision-making based on visual and haptic feedback enabled by the nervous system. In this emerging field of research, human gestures can be analyzed on a visceral level, allowing architects to explore answers to questions such as, how do we perceive external information? Or what decisions do craftsmen make based on their perception? These questions are highly contextual, since varying local traditions, tools, materials, and even postural conditions change the behavior of the craftsman. For instance, a stonemason is removing the sharp corners of a sewed stone in preparation for stone processing. In this example, the human eye notices the amount of material subtracted in the previous action, guiding the craftsman's decision-making regarding where to place the tool for the following one. The transition of high-skilled human crafts to robotic fabrication requires a thorough understanding of the gestures constructing the craft. Since the craftsman's knowledge is of tacit nature, a full analysis of such gestures requires motion capture and subsequent data analysis. The selected technique presented here is traditional stone carving that is typical to the Middle East. The tools used are the classic chisels, point, flat, and tooth chisels. In order to record a specific hand gesture of the craftsman at work, we use the Vicon motion capture system. A specific setup includes 7 high frame rate cameras organized around the carving table, allowing to document the motion from every angle. In parallel, the chisel is mounted with an adapter consisting of 5 markers. Each marker receives a unique ID that is used to construct the adapter in 3D and derive the chisel's position and orientation in space throughout the carving session. Following each session, the trajectories were reconstructed and exported as 2-dimensional arrays in a CSV format and visualized using Python. The data is then interpreted using a custom Grasshopper plugin and visualized in Rhino. The reading allowed to construct a continuous toolpath for observation and analysis, as well as to directly transform the human recording into a functional robotic toolpath. A computer vision application was developed, allowing to detect the total amount of material removed from the stone surface for each chisel stroke. A stone is a complex substrate to work upon. Its geometry is irregular. Its texture is uneven and porous. In addition, when force is applied, it behaves unpredictably. These aspects contribute to a high degree of uncertainty in a robotic fabrication context. This uncertainty is dealt with through a continuous sensing and motion correction process. To this end, the robotic cell is equipped with a stone carving toolkit, enable it to adapt as it operates in specific material conditions. The toolkit includes a high-definition camera, a depth and distance sensors, as well as a multi-tool end effector. The end effector includes a pneumatic hammer that connects to a variety of chisels and replaces the traditional manual hammer. A linear axis that brings the chisel back after each blow and replaces the second hand of the craftsman. And a shock observer that prevents damage to the robot due to the stroke impact. The sensing capacity enables the robot to see and feel the material in its environment. Employing this capacity, however, requires a specific protocol to facilitate the action. Locating, positioning, and timing a stroke is conducted in response to a specific material state rather than a predetermined motion plan. In practice, this is done through a client-server software architecture in which the robot runs a native loop program built to receive motion commands and handle interruptions initiated by the sensor data. In parallel, each sensor acts as a client, collecting information and updating the model. The information includes the surveyed geometry, detected forces, and collected images, which in turn are used to determine the adequate motion plan for each iteration. Prior to the first iteration, the robot enters a listening state, waiting for a command to be received. An initial point cloud is produced and converted into a detailed mesh. A carving plan is aimed at producing a circular crater, and an initial action length of 10 strokes is defined. In each carving iteration, the geometry is updated and an additional 10-stroke iteration is performed. This is repeated until the target geometry is achieved and the carving plan is completed. To conclude, facing a decline in manual craftsmanship in architecture, we explored the potential of future autonomous craft. To produce a tool that is autonomous in craft, we presented a 3-step framework. This included documenting the gestures of local craftsmen, augmenting a robotic fabrication tool with a custom end effector and sensor toolkit, and enhancing the fabrication protocol with material and spatial awareness. In this context, achieving autonomy in craft does not rely on increased precision, predictability, and repetition. Rather, it is rooted in the ability to contain imprecision, handle uncertainty, and support variation. While the former approach has previously resulted in favoring docile materials, the latter one opens the possibility for robotic engagement with a wide range of overlooked materials. Additionally, the global disappearance of historical crafts and local workmanships carries a risk of erasing fundamental cultural knowledge and practical skills. In an age characterized by an increasing proliferation of digital tools, preserving and transferring these skills supports the long-standing dialogue between the architects and the materials at hand. Thank you.